Okay, so today we will discuss on the last part of three-phase transformer of our curriculum, that is harmonics in the three-phase transformer. Then tertiary winding. Order of appearance may vary. Then sequence network and unbalanced operation. So first I would like to start with the problem of unbalanced operation first, and then depending on my need I will like to pick up one of the topic as per my own discretion. And so unbalanced operation, let me just share a problem here. So here is the problem. Three identical transformers are connected in star-star form. The means identical transformer, rating of the transformers are 100 kVA, 11,500 by 230 volt, 60 cycle per second or 60 hertz. Open circuit power consumption of individual transformer unit is 500 watt at power factor 0.155. Short circuit test data is like 217.5 volt when impressed across 11,500 volt winding. It causes a flow of 8.7 ampere current through the winding and consume a power of 1135 watt. Primary voltage is when the primary voltage is 15 kilovolt line to line. The secondary side loads are as follows. For each phase we are having equal amount of impedance, that is 0.6. However, one load is non-inductive, one load is means having unity power factor, another load is inductive and having power factor 0.866 lagging, another load is having a power factor 0.5 leading, right? So we have to find out the current and the voltage. Okay. So first what we should do, from the short circuit we have to figure out the transformer model also. So first let us try to okay. So here is the solution. Like from short circuit data we can calculate the series branch parameter. So what is the series branch parameter? Like short circuit power factor is how much? That is 1135 by this. So it is right. And what is the A or ratio of transformation? So equivalent resistance of all the transformer. Equivalent impedance, how to find? Like that voltage 217.7 by 87 into 1 upon 50 square. So that is 0.010 ohm resistance. All these are at low voltage side. This is the power factor. So that will be. What about reactance? All these are at low voltage side. Right. Now, with this, let us draw the diagram first. Like what we are having here, the primary side. Now this voltage is how much? 15,000, and also here it is 15,000. This one is also 15,000. So if you consider its corresponding one in low voltage side, you have to divide all these by 50. So what you will get? You will get this will result into 300 for each side. Right. This is the low voltage case, and do remember, as your primary is having constant line voltage, secondary line voltage will also remain same. Secondary line voltage will remain same. Right. Now let us consider that you are having this kind of situation where you are so I took some time to draw these diagrams. These diagrams are very important. Try to understand that, as I have already mentioned, that the primary side line voltage is constant. So your secondary side line voltage is line voltages are also obliged to maintain a constant proportional relationship with primary. So means it is this 300 is coming like 1500 by 50 will result in this 300. So there is nothing new here. However, what is the important thing to note, that all the phase we are having just a minute. So all these phase JD1, JD2, JD3 is equal to how much? We have already found it out. It is 0.06 plus J 0.08. Right. So this is the case. Now from the load information, I have written this is like this is A, this is B, this is C, and F is this blue color means components are indicating the load connected with one phase, like 0.6 is the magnitude of the load that is connected, 0.6 ohm. It is a pure resistive load. Now with another phase, what is there? It is 0.6 plus. So why I have always considered the series of individual transformer series branch in series with the load, because if you can recall, it was like for a simple system, for a single phase transformer, if you have a load like this, if this is your series branch, here you are giving V1, so what you will get here? You will get here V2 by A, and or you can consider here V2 by A, and here if you connect a load ZL, then the total current should be like I is equal to V2 by A divided by ZD plus ZL, right? So using that analogy only, I just wrote, or not wrote, rather drawn the all these. So you can understand here it is very easy that 0.6 one is pure resistive element that is having 0.6 ohm, that is connected with JD1 and being fed by phase A. This remember this all these side, they are virtual. There is no such physical winding is present. They are indicating the three terminals of the star connected secondary, and I just drawn them because just to indicate that this means the voltage between two phase, either AB or BC or CA, all these are obliged to maintain 300 volt because the primary line voltage is constant. However, phase voltage can vary. There is no such bound on the phase voltage, because remember the primary side is being fed by a source that is trying to maintain a constant line voltage. That is not bothered, or that is not concerned about how you will distribute your per phase voltages, right? So phase voltages may vary even in the primary side also. So what we will see here, JD1 0.6, JL1 is 0.6 ohm, this one is 0.5 plus J 0.866, this one is 0.866, like it here it should be 0.6. So now I have drawn a triangle. This triangle, it is easy to understand. This is 300 and this line is a perpendicular bisector. You can write it like E. Here this CE and B is equal to 150. However, this O is the shifted neutral position. Actually our neutral has shifted. Why shifted? Because due to load imbalance, the neutral is shifted to a particular direction. Now here this magnitude is how much? This is 300 minus if you consider this total is 300, then this length is 150 in the both side. Now if you consider this one, the means projection of point O on this BC line, then that point is, let us consider, that is X unit away from point B, and obviously then from point C it will be 300 minus x, right? So 300 minus x. Now as the three-phase voltage current can be represented in a two-dimensional frame or two-dimensional plane, so we can even for shifted neutral we can find its coordinate like x comma y. Now this is the height of the triangle. It is just like root 3 by 2 into 300. So that gives us this 258.9. That is the height. AE, the length of AE is 258.9. Now we have to express all the voltages in terms of neutral. Why this O is so important? Because here in this diagram, if you try to locate O, here it is the O. So once we can find out the voltage between A and O and B, O and C, then we can divide those voltage by the corresponding phase load. Means phase load means total load, comprises the series parameter as well as the load value. Then we will get the load current, like we will get IA, IB, IC, and we know that as they are connected here, they are bound to obey the KCL. So eventually we can write IA plus IB plus IC is equal to 0, and that can give us the result. In solving them we can find out the XY, and then obviously we can find out the voltages and current. Anyway, so let us write the voltage equation. So voltage equation, if we consider the voltage between O and A is EA, then how much it is? Let me just zoom this one. Yeah. Here you can see that you have to find out the length of this hypotenuse. If you consider this is a triangle comprises of O, A, and let it be P, then you have to find out OA. So what is OP? OP is, if you observe properly, what is OP? OP is your x minus 150. OP is your x minus 150. This is the distance OP. Now, if you consider away from B will result positive change in x, then your A is left. A is located left to the point O. Therefore, OP should be minus x minus 150. So we have to write it in that way. And what about the other component, that is AP, the height of this right angle triangle OAP, it is like 258.9 minus y, and that would be positive because A is at a means if you move from A to O, O to A will have a positive change of y. So let me write the equation. It is like x minus 150 plus what about EB? It is very easy for writing it EB. You are moving, you have to consider this triangle. Let this point be, this one be D. That is the projection of point O on this BC line. So this BD is how much? BD is x, but you are moving in a direction of negative x. So from O to B, so it is minus x as well as minus jy. Similarly, EC will be how much? EC will be minus, not minus, EC will be, see, here EC is what? Like you have to measure this value, like between O and C, that means you have to consider first CD and DO. So what is CD? The CD is like that one, 300 minus X, because here it is positive because you are your C is located right to the point O, so means from your perspective it is no sorry, C is located left to the point O, therefore it is increasing. Now this is 300 minus X. The way we have defined X, it is in positive direction, and this one is minus jy, right? So now accordingly we can find out IA is what? EA by ZE1 plus ZL1, so that is minus X minus 150 by J259.8 by, this will be 0.606 plus J 0.08. Sorry, it is 0.008, right? Similarly, you can find out IB. What about this value? It will become okay, sorry, so I made a slight mistake while placing the load diagram. Please correct, previously it was like these two impedance value was interchanged. Now I have placed them correctly. Now here obviously this is for our load, so what we are getting here, that is 0.526 plus J.306, and actually I'm not very good at doing all this in calculator, so I'm blindly copying from some book. It is a request to you that you please verify the magnitude of them using your own calculator. So that would be how much? 300 minus X minus JY divided by problem is that this book is by an American author and they are having ACB sequence, not ABC sequence. So I have to 60 Hz won't cause much problem in our understanding, but that phase sequence will surely cause distraction in our mind. So after solving what he is getting, let me write it from the book itself. It is minus 1.649 x minus 0.0218 y plus 253.01 plus J425.14 minus 1.649y plus 0218x. So one interesting things, okay, let me write the other current equation, then you will able to get it more clearly. Like we are having minus 1.415x minus 0.829y plus j 0.829x minus 1.415y and then minus 8.60x 0.860x plus 1.439y plus 258 plus j minus 1.439 x minus 0.860y so okay. Just a minute. So this is the value of current you will get. Now as I told you that finally we have to do IA plus IB plus IC is equal to 0. So from that you will have how many equations you are having? You are having 3 equations. However, there you can break them in real and imaginary part, and mind it that we are having 2 unknowns x and y, and finally clubbing all the real part together and all the imaginary part together will also give you 2 independent equation, while making the real is equal to 0 and imaginary part is equal to 0 will lead you the coordinate solution xy. So finally what they have written for real, it is like by making the real part 0, it is like 0.3924x plus 0.588y plus 511.01 is equal to 0. Another component is minus 0.588x minus 3.924y. So here solving this, you will get x is equal to 159.37 and y is equal to 114.36. So we got xy, then the remaining things will become very easy. So you will have to put everywhere the coordinate of xy, and IA you will get minus 12.28 plus J240.03. IB will be minus 320.31 minus J29.70. IC will be 285.51 plus J104. So if you convert them, what you will get here, it is 240.34 angle 92.2 degree 56 minute. Here it will be 321.7, 185 degree 18 minute, and here this one will be 303.86, 20 degree 1 minute. So these are the magnitude of current. Accordingly, voltage will be A is equal to minus 9.37 plus J 115.44, that is 105.82 94 degree 38 minute. EB is equal to minus 159.37 plus this is minus J 114.36, that is 196.16, 215 degree 40 minute. EC is equal to 140.63 minus J 114.36 it is 320 degree 53 minute. So here you can see the shift of the neutral point, and if you want to prevent it, what you need to do, you need to ground it. So if you ground it, then there will be no such deflection of your neutral point, and that is very important thing. Now another thing that is interesting here, if you notice the shift of current and voltage, you must have find out something very interesting here. So I wish that you can take your time to figure out what is happening and why so. So if you do that, you will get a better understanding why and how this kind of means load shifting takes place. I want that interested student should ask question on this, that what is the interpretation of these different IA, IB, IC. Okay, by solving equation we are getting this, but what is its physical interpretation, that we must understand, right? So here, one thing you must have noticed that when we started it, that it is a problem of start transformer. So this is a problem with start transformer, that phase voltage can often change from their means normal value to some different value. Now let us consider the concept of sequence network. In your class, I have already discussed the basic concept, like if we consider, I ask you to express the harmonics in that formula, like if the order of the harmonics is n, then you try to represent this like 3m plus q or p, whatever it was. So what was the value of m is equal to, like m can be anything, any natural number, 0, 1, infinity. P should be like, P is within the set, right? So in that way, if we find, we should take P in such a way, like if we have say n is equal to 23, then we can express it like n is equal to 3 into 8 plus minus 1. So that if p is equal to, if we find using this formula, if p is equal to minus 1, then that is negative sequence. If this is 0, then that is 0 sequence. This is plus 1, then that is positive sequence. I told all this in a very intuitive and casual manner, rather the serious formulation of this concept is required, and that is why let us consider in sequence network, what do we consider? Positive sequence is what? A set of balanced components which have a positive time sequence same as that of our fundamental harmonic sequence. Then B is, sorry, that second number is that negative sequence, a set of balanced components which have a as an example, you can consider like 5, then 11, 17, 23, 29. You can keep on adding 6 and you will get the odd order harmonics that is having negative sequence. Why we are considering odd order? Because we have already discussed that our windings or transformer they are so constructed or that topology of the circuit is such that they always produce waveforms having half wave symmetry, irrespective of whether it is an even function or odd function. They will always maintain half wave symmetry, and therefore whatever harmonics component will be present in your means total waveform, that will always be like odd order. That is why we are not considering like harmonics like even harmonics, like if you do 5 plus 3 you will get 8, but we are not considering that. We are only considering the odd order harmonics, right? Now here, then the third one is that a set of equal components all having same time phase. Now if we want to draw the diagram, then it will be like this is your positive sequence. Say fundamentally you are having this. Or another positive sequence is A7. Obviously you can get the all positive sequence network by adding 6 with your means keep on cumulatively adding 6 with your fundamental, and you will get all the order of positive sequence harmonics like 1, 7, 13, then 19, then 25, then 31, all are positive sequence harmonics. And here, because they are maintaining the same phase sequence, the negative sequence will be like and zero sequence is like generally we try to confine ourselves within the first 7th harmonics line, but some cases we go up to 19, 17 like that. Anyway, this is not our discussion. What we can say that, like if we have a balanced voltage, like or rather unbalanced voltage, let me draw some unbalanced voltage like you can also read it like VV, VC, VA. So what we can write like now, one thing it is clear that here we are considering the voltage, and it is like we are considering star. Now if you consider the star connection, then first let us not consider the means zero harmonics or zero sequence harmonics. Let us only consider we can write VA is equal to what? VA can be written as V1P or VAP plus VAN. VB can be written as VBP plus VBN. P for positive, N for negative. VC can be written as VCP plus VCN. Right. Now, what we know that we can write further that VAP is equal to your VAP angle 0 degree. Let us consider. Now, as they are balanced, what we can write VBP is equal to magnitude remains same, only change in angle is minus 120 degree, and that we can write it by using an operator, that is A inverse. What is A inverse I will discuss, and the other one will be VCP is equal to VAP. So if you are curious about A inverse, then it is like you can write it this minus 120 degree like cos 120 degree minus J sin 120 degree, and then you will find that this A is basically like that this is our E inverse, right? So this A inverse, if we want to have in our picture, then what we should do, like just a minute. And similarly we can write our VAN is equal to VAN 0, then VBN is equal to VAN angle plus 120 degree. So it is VAN A instead of A inverse A, it is A, and VCN is equal to VAN plus 240 degree. Plus 240 degree means minus 120 degree also, means actually it is taking the position of this. So it is VAN square, right? Now with all this, what we can do here is that trying to understand one simple thing, that if you add all of them, like being let me write it clearly. Similarly, VAN plus, right? So both of these set are 0. In addition, like what you can write, that VA plus VB plus VC is equal to 0. So from this, let us rewrite once again the equation, like VA is equal to VAP plus VAN, then VB is equal to VBP plus VBN is equal to VAP A inverse plus VBP A, then VC is equal to VCP plus VCN is equal to VAP A minus 2 plus VB Here it is AP, VAN A square, right? So this is all. Now what we can write from this, it is very clear that we can write our, so if we want to find out what is our VAP, because VAP is not physically realizable thing or physically means you cannot directly get it, rather you are getting the unbalanced voltage VA, VC. What we can write from this, if we add, then what we will be getting, like you can have VAP plus VAN, then you can do what? You can do A into VAB, that will result in what? VAP, sorry, VAP plus VAN A square, then you can do A2, here it is VC, then it will become again VAP plus VN A to the power 4. Now A to the power 4, what is A to the power 4? A to the power 4 is like A to the power right. So e to the power j2 pi by 3 4. Now if you see it, then e to the power j2 pi by 3 4 means what? Like you can write it is like e to the power j 2 pi by 3, that is a. So this will become again a. Now what we know that being a balanced set, what I wrote here, that VAN means here you can write it like this. True. This line implies this line. So if that is the case, then if you add this, then they will vanish, and you will get VAP is equal to 1/3 VA plus AVB plus A square VC. Accordingly, if you try to find out the others, like what is your VBP, VBP will be, so this is your VAP, and VBP is equal to magnitude wise VAP is equal to VCP. We can prove this also just by considering the proper shift operation. Now similarly, from this equation we can get the corresponding value of VAN. Like instead of multiplying them by A, we should multiply them by A inverse, A to the power minus 2, and then from here we will get that they will cancel out this like whatever is, oh god, whatever is there, it will be cancel out, and we can get the similar equation for Vn. So what will be the change with VAN? VAN will be VAN, sorry, not, it will be VA plus VBA inverse plus VCA to the power minus 2 by 3. So you can understand here that it is all a square, and here it is a inverse a square, right? So this is the case. Now let us take one numerical example that will clear our idea. Like V1 is equal to okay, then one more question can come, that how to find out the zero sequence. Here one thing we can see from the diagram, that here it is VA plus VB plus VC. If they are not equal to 0, then the zero sequence voltage will be just addition of them. If you add them, you will get the zero sequence voltage. Plain and simple addition. Why this is so? Because as zero sequences are directed in the, means they are unidirectional for all the three phases. So what you will have here for zero sequence, they won't cancel out each other. Why your positive or negative sequence, when you add them, cancel out? Because they are balanced, and there is a shift of 120 degree from each other. But for zero sequence, they are in phase. So if you add, what you will get, that is your zero sequence, means you can sorry, it should be VAZ is equal to VBZ is equal to VCZ. All of three are in phase, right? And here, while writing AZ, here we are indicating all the means zero sequence. Like it can have third harmonics, it can have ninth harmonics, it can have 15th harmonics, it can have 21 first one harmonic, it can have 27th harmonic, like that. All we are not doing any division here. So let us go to the example. V2 is equal to minus 800 plus J100, and V3 is equal to minus 1100 plus minus J270. Now obviously it is clear from their expression that their summation is not 0. So you can find out V0 or VZ. Some people also use it V0, V1 plus V2 plus V3. So that will give you minus 300 minus J40. So that is 302.6 with an angle minus 172 degree 24.3 minute. Now V A or V1, no V like VAP, this is VAZ. VAP is equal to what? VAP is equal to 1/3 1000 plus J50 plus minus 800 plus J100. Then you have to append A. So what is A? A is e to the power J2 pi by 3. Then here plus minus 1100 minus j270 e to the power j4 pi by 3. So whole bracket. So if you solve, you will get it is like 543.19 plus J131.6, that is 558.9 angle 13 degree 37 minute. And similarly you can do VAN. Only thing, you have to change all this by minus 2 pi by 3 and you will find like 756.6 minus J 41.6, so it is 757.9 minus 3 degree 8.8 minute. Now here one thing you must note, that here it is very unlikely that your negative sequence is dominating over the positive sequence, because here you can see that the VB and VC, both of them are having negative parts. So that is what giving rise of the dominating negative sequence component. But in reality what we will observe, that positive sequence component always dominate and negative sequence component are not that strong, although it is present there. Another thing here you must notice, that here all these, they are having some angle, like what I am trying to say here, like this is having the AP, it is having some angle 32 degree 37 minute. That means it is leading your FS. The reason behind this is it is not the balanced one. That is why it is shifted from, if you consider balanced network, you will find only VAP is present and it will exactly coincide with your FS. However, what happens in case of unbalanced one, you will have VAZ, VAP, VAN, and then that will cause some unbalanced component there. Now in the next part we will consider the tertiary winding. Okay, so I have made a slight change in the course plan. Instead of considering other things, let us consider or try to understand the zero sequence network for different transformer connection. Why zero sequence is so important? Because unlike others always maintain, like if you consider, there is also an important concept in transformer engineering, that is oscillating neutral. Right. So what happens in case of transformer? Suppose if you have a three-phase winding. Now that neutral of this three-phase winding, it is your like, if you consider the positive and negative sequence components, then they will find that for positive or negative sequence component, neutral will remain same because they are 120 degree apart and they are balanced voltage set. probably there was some sound problem. So what I was trying to tell, let me tell you once again. Today, instead of considering other, we are going to discuss the concept of your zero sequence network, and first of that we will like to consider the case of oscillating neutral. When your transformer is Y connected, then what happened to the transformer? Suppose if you consider the positive sequence or negative sequence, those sequences are balanced and they are 120-degree apart. So at any time point, if you add them, what you will get, the resultant you will get, it is 0. But in case of your zero sequence, they are rotating in means all the three phasor of zero sequence are in phase. So what they how they work, like while all these phases are executing a sinusoidal rotation, these people are doing like this. In one instance they are here, in another instance actually they will form a, you can say that it will form a kind of circle like this. So in next instance all of them will come here, in other instance they will find them here. So basically what they will form a constant circle around your neutral point. However, one thing you must not forget, that like zero sequence of A phase will act with the zero sequence of A, like here if you consider your zero sequences are like this. So how they will work for A, if this is your positive sequence and we are considering only zero sequence, no negative sequence, then your resultant of A will be how to find, you have to add it, right? So you will get something like this. Similarly for this one you will get for B phase, you will have the B phase zero sequence is also aligned in similar way. So you will have, if you want to add them, you will get something like, just by means of parallelogram law of vector addition, you can figure out their resultant. So you will find it somewhere here. Now what about, sorry, this is the resultant B. Similarly for C, what you will have, for C you will have so now what you can see, that the total they have shifted in such a way that your neutral, instead of having here, your neutral comes somewhere here. Now because in neutral you have to make all the means addition of all the voltages is equal to 0. Now here if you consider some other point, then you will see that at some other instance when they will be in this direction, your neutral, instead of being fixed at a particular point, it will make a complete rotation around your actual or neutral point with certain voltage, and that will cause a huge means appearance of a huge unbalanced voltage across different phase on different times. So that is not means desirable, and that is why zero sequence is most alarming, because they all these three are in phase. So now we will try to study the transformer different configuration zero sequence component. Now let us consider the case of like our case of individual connection, typically we are going to study a few connection like we have already discussed YY without neutral. So in case of YY without neutral, we have means understood the principle of like that kind of oscillating neutral may occur. Now here one thing I would like to make you clear, that suppose if you have do remember a few things like our line voltage in case of a three phase transformer. If your primary is connected to infinite bus, then the secondary then the first of all let me write, then the primary voltage will always be and also the secondary line voltages will remain sinusoidal. Now what we can have, we can have phase voltages are distorted or line currents are not sinusoidal, or phase currents are not sinusoidal. Okay, so now one more thing I would like to tell you, that if you have a balanced star connected network without or with acting with only positive and negative sequence component, then what you will observe if you have a star connected network like this. Now if you connect one ammeter with the ground, then you will see that until unless you have means any zero sequence component present in your phase current, if no zero sequence component is present in your phase current, then this ammeter will always read 0, like no zero sequence implies this is quite natural, because whether you are having positive or negative sequence, when you phase current, positive or negative sequence phase current, because they are means for a balanced three phase operation, they are cancelling each other. So at your neutral, their sum always will become 0. But if you consider your third harmonic current, all of them are in phase. Like if this is I3, this one is also I3, this one is also I3. If this is some sine or cos omega t, this will also be that exactly same phase will be maintained by all these three currents. So therefore they are in phase, and in case zero sequence current component is present, then this ammeter would read by virtue of power definition, all the sequence currents are equal in magnitude in all the phase. So 3 into 0 sequence current per phase will be read by this ammeter. Similarly, if you talk about voltage, then you will see that in case of a delta connected network, if you break apart and connect one voltmeter here in order to validate KVL for this one, like when all you are having plus and negative minus, but when zero sequence is present, zero sequence voltage is present, now let me quickly remind you what we study for single phase transformer, like for a sinusoidal voltage. In that case there was no story of line voltage, only phase voltage was there. The flux is sine wave, and if we want sine wave flux, we need a magnetizing current that is peaky in nature. So here I am not writing it because I cannot write it for a single phase one. This positive, negative, and all these are applicable to three phase in the context of three phase analysis. It is meaningless to describe this in the for context of single phase, but you can understand when you connect all the three transformer, if you form a transformer bank, then also the individual transformer, they preserve their individual characteristics. There is no such huge change in that individual transformer characteristics, right? So for all sinusoidal voltage, like all sinusoidal voltage, you can read it like when you have a primary transformer, that is primary side is connected in delta. In case of delta, what we know that line voltage is equal to phase voltage, and if your line voltage is means obliged to follow a sinusoid pattern, then obviously your phase voltage has to be sine wave. There is no other choice. However, the story is different for star connection. What is the story? Like if you have a sinusoidal magnetizing current, like if your primary side is connected in star and the means neutral is not grounded, then obviously what will happen? A sinusoidal magnetizing current will flow, because there is no path for the third harmonic current. So how the third harmonic current can flow through your winding? Therefore, the current that is drawn from your source will be sinusoidal in nature. However, that sinusoidal magnetizing current that will create what? The flux wave will become a flat top. So what would happen if that flux wave become flat top? Then there will be so what is the key thing here is that if flux is sine wave, then you need a peaky magnetizing current, or otherwise you have zero sequence component present in your magnetizing current. Or if current magnetizing current is sinusoidal, then your flux will be flat top and induced EMF will become peaky in nature, right? And there is no harm, because if you consider the star winding, phase voltage phase voltages are not obliged to be wave like a sine wave, and that exactly corresponds with your theory of oscillating neutral. Like phase voltages are different than they should be in case of only the positive sequence fundamental order harmonics are present. You can have a particular value of phase voltage that is balanced, and 120 degree means time phase wise there is a difference between each and every phase, that is 120 degree, but here it is totally different. Now let us consider an individual connection, and let us study what is their means pro and cons of them. Now let us consider first the case of y. So y, what we will get? Like in a nutshell, what we can say that So what we are getting here, YY without neutral, no zero sequence current present. So therefore line and phase current, phase magnetizing current we are considering with no load, line and phase magnetizing current, they are sinusoidal. Line voltages are also sinusoidal and phase voltages are peaky in nature, right? So if this is the case with our means star connection, right? And if you notice carefully in that principle of third harmonic oscillation, it is like the means speed of oscillating neutral is 3 times the fundamental complete rotation. Like how to find out the speed of the fundamental? It is like for a p-pole system, it is like 128 by p. Now, or if you are not getting that, you can also consider it is like 50 cycle per second. So it completes cycle means means it completes 50 cycle, or one cycle is completed at a time 1 by 50 second. However, in case of our third harmonic oscillating neutral, the neutral is rotating at a speed of means 150 cycle per second. So that is a very dangerous case for this oscillating neutral. Now we will consider the, if you okay, one more thing here, it is important that we try to draw their corresponding zero sequence current path. So what we will find here, the zero sequence current cannot flow through our means zero sequence impedance. If we consider it like x12, so x12 it is neither connected with 1 nor it connected with 2. Right, now consider our YY with neutral. So in case of YY with neutral, means it is neutral grounded. Then what will happen? Let me write. The zero sequence current will be present in phase and line voltage, line current. In addition, that neutral wire or neutral ground wire will carry 3 times of the zero sequence current. Here, due to the presence of zero sequence current, your magnetizing current is non-sinusoidal or peaky. Therefore, flux and EMF are sinusoidal in nature, and that is a very obvious thing. Just we are stating the things in a different manner. Like if you have a star-star connection, if you ground one of them like this, right? What would happen that can any means can this phase voltage we can have a different phase voltage other than a sinusoidal one, because the neutral point potential is constant. Your line is connected with lines are connected with an infinite bus bar. So obviously whatever voltage phase voltage you will get between constant to constant potential point, that will also remain constant, and the only way to get a constant voltage is that the voltage must be in this context voltage must be alternating in nature, and that is must be a sinusoid, otherwise how can you get a constant voltage? So this is one stable configuration. Now let us consider another one, that is dy. What actually happen in reality, that sometimes from generator we it is like what is the significance, like here from generator it is we know that handling high current, high line current is easier with delta. So this side it is low voltage, then you step up in high voltage form, and then you transmit through transmission line, sorry, and then this is the transmission line you connect, and your this is primary low voltage side, high voltage side, then again you receive at high voltage, and then you step down to low voltage and make it in delta, because whenever you want to step down you have to consider a flow of high current through your winding, because kVA cannot be altered, right? So if you want to keep kVA constant, then for low voltage you must have a high current flow through your winding. So for dy, what is the case for dy? If you apply sinusoidal voltage, sinusoidal line current but what happened, the funniest thing is that delta provide a closed path for zero sequence current, therefore phase currents are not sinusoidal. Now phase currents are not sinusoidal, and there is third harmonic EMF exists in the phase winding that constitutes a flow of like current through our delta path, right? So phase currents are not sinusoidal, and that these are the delta y case. Now, if you consider the what happened to your start side, if you ground the neutral, then there is a fine that all third harmonic current will go to ground. But if you do not, then there will be a small chance, because that primary side third harmonic current will also try to flow, like whenever there is a third harmonic current, it is basically what I am trying to say, that Ni by reluctance is equal to flux. So if you got third harmonic current and flux, they will also share the linear relationship, because third harmonic current magnitude wise it's very small in compared to the fundamental harmonic current. So therefore it will maintain a linear relationship. Now, if there is a third harmonic current present in your phase current, magnetizing current, there will be a third harmonic flux will also present, and that third harmonic flux in the primary side will also induce a third harmonic flux in the secondary, means that third harmonic flux will also link the secondary side winding, and that will cause a third harmonic voltage across your secondary side phase. Like this is for primary, you may find that secondary side voltage is due to the presence of that means third harmonic current. But if you want to avoid it, now obvious way is to ground your neutral, and so in case of dy we have okay, one thing I forgot to discuss, that when we are having this, then it will be like just a minute. So here it will be like basically this XOR 2 is like, and both are this for third harmonic component, right? So when you ground them, so if you unground anyone, then there should be like, or if you do the reverse, like got it. So this is the case. Now obviously one question may come in your mind, that if there is no such third harmonic means voltage, then how the third harmonic current is flowing? Obviously there must be a third harmonic voltage, and like if you take the ratio of third harmonic voltage and third harmonic current, you will get the corresponding third harmonic impedance. I know this sounds a bit confusing, but when I will start solving numerical problems, you will understand it. So for dy, what you will have, for dy, it is like delta provides a closed path for your circulation of third harmonic current. So you can consider that delta y is like the primary is delta, that side is grounded, means primary has no such connection with the secondary, but the EMF induced across it can flow to the ground. Means this is a case of virtual ground, because all the EMF are circulating inside your transformer primary part, right? So if you have grounded like if you have YD, then it will be changed, like it will come to this side for YD with isolated neutral, and YD, if your Y side neutral is earth, then obviously you need to short these 2 points, right? And if you have, okay, so this is dy, yd you can easily figure out by yourself, like in case of yd, okay, let me write it, otherwise you will get confused. That try to understand this, like magnetizing current is primary side magnetizing current apparently it may appear in your mind that primary side magnetizing current will be sinusoidal, as the neutral is ungrounded. But then what you must notice, that your secondary is delta. So secondary delta will provide a closed path for third harmonic current. Now if secondary is carrying a third harmonic current is flowing through your secondary, you know that secondary current will produce a demagnetizing action, and primary must compensate that demagnetizing action. So in turn, primary current will be non-sinusoidal to counterbalance the non-sinusoidal secondary current MMM. So therefore flux will be sinusoidal, and that line at phase voltages like, even if you do not understand anything about harmonic, if you have a common human brain, and if you know how to use your gray matter, you can always figure it out. Just means if you are having means a lack of experience, may take some extra time. Like what is that? In case of star delta, see, your line voltage is the secondary side phase voltage. Now primary side line voltage is connected with the infinite path, so that must be sinusoidal. Secondary side line voltage that is obliged to maintain a means constant like proportionality with primary side line voltage. So secondary side phase and line voltage will also become sinusoidal. Then obviously your primary must be primary side voltage also must be sinusoidal in nature, and therefore the flux. Now what happened in case of our so another case is what? DD. Okay, so DD, what will happen? Line current, sinusoid, phase current, non-sinusoidal, phase and line voltage are sinusoidal. Okay, and what about the third harmonic zero sequence current circuit? So let us consider a few problems. Well, so let us consider the first problem. This three-phase star delta transformer, its delta is open circuited. A voltmeter placed across the phase winding AB reads 260 volt, and when placed in open delta it reads 300 volt. Like when you connect between AD, it reads 300 volt. Find the reading of the voltmeter if it is placed across BC and BD. Okay. So what is the funda? It's very simple. The delta is open circuited. The voltage across winding AB is what? AB is this much, is what? V1 square plus V3 square plus V5 square plus V7 square. We are considering up to 7th harmonic voltage. So what we can write that 260 square is equal to this V1 square plus V3 square right. Another thing what we can see that when we place the voltmeter across AD, so what is the reading AD? This reading AD is, so V3 will be how much? 300 by 3 is equal to 100. So therefore here what we will get, like from this line what we can write, I just do not want to go to the next page. So here we know V3 is equal to 100, therefore you can find out root under V1 square plus V5 square plus V7 square. So that will be how much? That will be 26. Now here it will be how much? That V1 plus V5 plus V7 will be present in VC. So this will give you some value, like you will get so in my calculation it is coming 240. Please check by yourself. Now what is the voltage across our EBC? That will have the same voltage across EAB. So that means BAB is equal to BBC is equal to our VCD. However, if we try to measure VBD, there will be a slight change, like VBD will be how much? See, AD you are getting the 3 means V3 is present here in your means this is your AB. So when you are trying to measure BD, then once here BD can be written as like form. BD is like VAB plus like VBA plus VAD. So if that is the case, then you will find that VBA is what? VBA is this one much, like this 260 square, or means in a nutshell we can write it like this, like 240 square plus 2 into 100 square, because there will be 2 V3, right? So 2 V3, so that will be giving us that 312.41 volt, right? Now let us consider that other problem. So please have a look. The secondary star supplies power to a purely resistive load with one ammeter voltmeter connected as shown in the reading of the ammeter and wattmeter is 9 ampere and 810 watt. The line to line voltages are balanced. So here it is clear that this line, this lines are basically carrying the third harmonic components, right? So if that third harmonic current is flowing, the magnitude of 3 times of third harmonic current is 9A. So your third harmonic current is 3A, and from that you can find out the like your wattmeter reading. You can find out the voltage between them as well as the R. So 3I3 is equal to 3I3 is equal to 9. That implies I3 is equal to 3. Now load is purely resistive, therefore what we know that third harmonic voltage cannot means interact with the fundamental harmonic component, so it will be 3V3 into I3 into the power factor. So now what is the power factor? Then this load is resistive, this power factor will be 1, so 3V3 I3 is equal to 810. That implies V3 is equal to 90 volt. So the value of these resistors are I hope you are getting this problem, like 90 volt we are getting between these two. Now this is total 9 ampere current, because you can consider like this current coil, you can consider that every phase is in parallel. Like what I am trying to say, like you can consider this problem so here the current is one phase, one arm, the current is 3 ampere, power is 270, voltage is 90, therefore R is 270 by 3 square. You can find out it is 90, sorry, it is 30, right? Now let us consider another problem. So what does it state? 3 identical single phase transformer are connected in star on the primary side. The line to neutral voltage due to fundamental component of flux phi 1 is 200 volt. It is found that the third harmonic flux, first and fifth harmonic flux are present. The primary to secondary turns ratio of each transformer is 1/4. So if this cause a 200 volt, then what about the third harmonic and fifth harmonic flux? One thing you must remember, that the third harmonic, although it is being 20%, but what about its voltage contribution? Do remember, it is like your voltage, your V3 is related to third harmonic, like sine or cosine 3 omega t. Therefore, when you differentiate, it will come like 3 omega will come here, and this will become some cos or whatever. So what is my point, that when you are considering fundamental, then fundamental is like V1 So it will be like this. So in case your third harmonic flux is 20%, the voltage will be 3 to 20% of your primary side voltage. We are assuming individual linear relationship, like although the total circuit is non-linear, and that is what caused this kind of harmonics, but we are assuming that it is the proportional relationship still valid between primary and fundamental and its primary voltage, then third harmonic and its voltage. So in nutshell, what I am trying to say, if it is 200, then the third harmonic voltage will be 3 into 20%, like 60% of the whole thing. So basically 120 volt. And similarly, your fifth harmonic will be 5 into 4%, that is 20%, right? So keep all these things in your mind. Now, what we have V1, that is 200 volt, V3 120 volt, V5 40 volt. Correct? Now EMF, secondary side EMF will be how much? See, the primary to secondary turns ratio of each transformer is 1/4. Like, so secondary will be a step up case. So correct? Now here is the issue, that if the secondary side is star, calculate line to neutral voltage and line to line voltage. So while calculating the line to neutral voltage, you must consider the effect of third harmonic, and while calculating the line to line voltage, you have to drop the third harmonic time. That is the basic issue with this problem. So line to neutral will be how much? So all square, this should be 800. Actually, I hate this kind of things where so much means effort we need to spend on calculation. Now, as I said, that what about V line to line? Both are secondary. This is secondary. This is also for secondary. V line to line, secondary will be how much? That will be √3 of, here is the beauty, 800 square plus 160 square. This term should not be considered while calculating the line. So what you will get? You will get, it is like 1413.04. So now you must have understand the concept of oscillating neutral. Although you may say that, sir, it is line and neutral, means line and phase, they are also in proportion. Obviously, if you find out this ratio, you will get a constant proportion. But what is the catch here is that your line means phase voltage, it is considering means unidirectional rotating, not unidirectional, rather means zero sequence component that is continuously rotating at a 3 times of fundamental frequency. So here you will have an oscillating neutral. So what is this 9/4? This one, like if you consider the line voltage, then all these are and if you consider this 946.57, suppose neutral is shifted in this direction, so this will be this much. Like here it is this side is all the component you are having V1 plus V5 and the base is V3. So that is how it is coming. Like this side is and this side is V3. So when you will do, you will get it like V7 is not present. So because V1, V5, V7 all they are appearing in this way because they are either primary or means they are either positive or negative sequence. So either they will act together or they will oppose each other. Like first and fundamental and fifth harmonic, they oppose each other. Fundamental and your seventh harmonic, they act together. So it's like that. But when it is about V3, then you will always get it like this. Fine. Now so the secondary V line to line is how much? 946.57. No, sorry, this is here. This is 1413.04. Right? Now, what are the other part? The secondary is connected in delta. So, if the secondary is connected in delta, what would happen? The line voltage will be free from third harmonic voltage. It will become E1 square plus E5 square, that is so when the there is another part, no? Open circuited delta. Okay. So in case of open circuited delta, what you should get? In case of open circuited delta, it should be 3V3, that is 3 into 480 volt. It is 1440 volt. Right. Now see, if the primary neutral is connected to the source neutral and secondary is in star, so if you calculate the primary neutral, that will always stabilize the things, and your secondary will have what? Will have 800 square plus 160 square, so it will be 815.84. volt, and secondary line voltage will be root 3 into root 100 square plus 160 square, that is 1413.04 volt. Fine. Now the D, if the secondary winding is arranged in delta, find the voltage across the secondary circuited delta. When your primary is neutral is grounded, there will be no third harmonic voltage, and therefore the open circuited delta for D, the answer will be 0. Right? Now let us consider this problem. We are having a bank of delta star power transformer is connected to a bank of star star distribution transformer. The secondary of the power transformer is solidly grounded, and the secondary line voltages are sinusoidal. Obviously it has to be. The two neutrals of the distribution transformer are not grounded. Okay, a voltmeter connected between ground and the primary neutral of the distribution transformer gave a reading of 3000 volt. Fine. Calculate the effective values of line and phase voltage across the secondary of the distribution transformer, for which the primary to secondary turns ratio is 30. Okay. So it is clear from the figure, it is 11 kV, it is appearing. Now 300 volt present between transformer neutral and ground is due to third harmonic voltage. So what we can write, that the component of in the secondary phase winding will be how much, that third harmonic voltage will be so this is 100, right? For distribution transformer, fundamental component of primary phase voltage, because line voltage has to be constant, and line voltage will be free of, you can consider that line voltage is free of third harmonic voltage. Therefore you can find it out, like V1 is equal to how much, 11 V1 PD is equal to 11,000 by root 3 is equal to 6351 volt, and V1 is D, and distribution transformer is D, so it will be 6351 by 30, so that means it will become 211.70 volt. So what about the secondary phase voltage will be V1 is D plus V3 is D square, so that will be something like 100 square 211.70 square plus 100 square, so that will be something 234.13. However, line to line voltage will remain sinusoidal, so that will be root 3 into that is line to line voltage, that is 366.6 volt, right? So this is one problem. Now consider the last one in this row. A bank of three identical unity ratio transformer is connected as shown in figure. At no load, the readings of ammeter A1 and A2 are 0.75 ampere and 0.46. Clearly, A1 is carrying the line current and A2 is carrying the phase current together with the third harmonic current. But third harmonic is absent in the line current. If the secondary is also connected in delta, what will happen to the reading of that A1, A2? So here so what about these three? These three is equal to 0.75 by root 3, or that if you calculate should give you 0.433 ampere, right? Yes, 0.75 by root 3. Now, what about I3? From these two equations, you can figure out I3 is equal to 0.433 square minus 0.46 square minus 0.433 square. So that will result I3 is equal to 0.1553 ampere. When the secondary is also closed in delta, the third harmonic current will flow both in secondary and is primary. So what will happen, that you can observe a slightest reduction in the reading of A2, because now your secondary side is also providing a path to circulate your third harmonic component. Therefore, means this one you have to visualize that why it should be A2 should be reduced when you connect the secondary in delta. Like when it is in only primary is delta, then the whole third harmonic current is circulated through the delta winding primary side, but there is no flow of third harmonic current in the corresponding secondary side. But when now obviously you may raise a question that why the third harmonic current is not affecting our secondary side. When the secondary side should have a proportional MMF for third harmonic. So in that case, I would like to request you think about it is not only the MMF but the flux that actually control your EMF production. So primary and third harmonic together produce the secondary side winding, means the total flux, and that flux will interlink with your means secondary side winding. Here, do not try to just apply the normal scenario, the linear case when you are getting always a proportional, means demagnetizing effect produced by your secondary or primary. Not like that. You have to be a bit more, means you have to understand this configuration. You have to empathize the transformer situation. Until unless you can feel it, there will be means you cannot succeed in this area. Now, obviously, A1 will remain unaltered. When you will connect the primary in star, then what would happen to the ammeter? The ammeter reading A1 will remain same, and there is no scope of connecting A2. Actually, this is the problem with this book, carelessly written book. Like if the primary is connected in star delta, so if primary is connected in star, then why rather how we can connect that A2? Where should we connect that A2? People are like, means whether A2 will be placed in a particular phase or in a winding, no consideration about that. Okay, so I think you can means understand this problem and do it by the remaining part. You can solve it by yourself, because I am getting very bored with this kind of question. Like you must mention that where to connect it to when you convert it in star. Anyway, so you try this one, and one thing is very clear, that if you connect the primary in star, then what will happen? If your neutral is not grounded, there will be no third harmonic current will flow through the primary. Now current in the secondary will be how much? Current in the secondary will be that third harmonic current will flow. Okay, now we will go to tertiary winding. So let us consider the last topic, that is tertiary winding. What is tertiary winding? Before going to tertiary winding, let me discuss what is the problem with 5-limb or shell type transformer, 5-limb core or shell type transformer, or 3-limb core type transformer. When they are connected in star-star form, Y-Y form with ungrounded neutral. So what happened in case of a 5-limb or 3-limb? I'm not going to the construction. Just one thing I would like to make you understand here, that in case of shell or 5-limb core type transformer, the third harmonic flux get enough path to, means enough iron path to circulate through the core. However, in case of 3-limb, I am trying to show you a picture that will make it clear. So here is the diagram of this one transformer. Both are transformer, one with 3-limb and another one with 5-limb. Here in case of 3 limb, you can see that because these three they are unidirectional, like A, B and C, all these are producing third harmonic flux, but all these three flux being unidirectional, they are not getting any path to means we know that flux path forms a closed loop. So it's almost like current, as like current needs a closed path to circulate. Likewise, flux also needs a closed path to circulate. However, here we can see that these third harmonic flux, they are not getting any return path, because suppose if the limb which is connected or which is wound with your Fs winding, whatever third harmonic flux it is producing, if that third harmonic flux tries to find its return path through here, through B, then the third harmonic flux of B that is equally in magnitude and means that will opposite, right? It is not the case of normal flux, because normal flux are exactly 120 degree apart, like due to fundamental harmonics or any other means that is not an integral multiple of 3, then you will see that all the flux produced by the one set of harmonics is getting 0. So they always can find a return path. However, for zero sequence flux, they cannot, because they are unidirectional, they cannot get an, so they have no other choice other than leaving this core, means transformer core, and find a path through the means iron tank or anything that is the chamber that is enclosed the transformer. However, that it involves an air path, and that is air path of having very high reluctance, that makes the means flux means effect of this third harmonic flux very quick. However, here what we can see that in case of 5 limb, these flux are getting easy path for return. These two side limb, they are not associated with any winding. So what third harmonic flux are doing, they are getting an easy path to return. So what is the conclusion of this? That third harmonic flux is dominant for 5 limb core construction or shell construction, and not so dominant and not so harmful for 3 limb case. So in case of neutral, oscillating neutral problem, what you will observe that in case of 3 limb construction, if your neutral point is like theoretically, or in case of ideal case, your neutral point should be here at centroid, but then there will be a slight shift because of that third harmonic, and say neutral come here, and you are having this sort of unbalanced phase and phase voltages. This is for 3 limb. What you will observe for similar kind of means loading or whatever, you will see that the deviation of say the electrical rating of both the transformer are equal, and you will see that there will be a huge, means if this is say this is the centroid. Now actually problem with this pen tablet is I cannot draw it with the scale. That is what makes it very difficult for me. So what I am trying to say that if this is the centroid, then what you will observe that in case of a 5 limb, your new neutral may come anywhere like this, and you will have, so if you measure the corresponding shift of neutral for 3 limb and for 5 limb you will see that in case of 5 limb neutral perturbation is quite high in compared to 3 limb. So 5 limb, and also the same kind of things happen in case of shell type transformer. Shell type transformer due to its construction provide extra iron path for the flux to circulate like for the third harmonic flux. So that is a problematic things. So in order to circumvent this issue, what we do, we use a delta connected tertiary winding. What is that tertiary winding? Suppose you have one star connected primary and another star connected secondary. Now what you can do, you just introduce a tertiary winding in between. It is quite common that to connect tertiary or form tertiary in this delta, sometimes this tertiary winding we also call it stabilizing winding. Why this is stabilizing winding, I will discuss. So what happened due to the presence of this tertiary winding, you will understand that these are equally linked with your primary side, and it provides a path of third harmonic current. So if we take a single phase basis, then what we can show that single phase basis equivalent circuit will be like you are having one primary winding with R1 and JX1, and you are having two secondary winding, like one of that of tertiary winding and another one is of due to your normal secondary. So this is R2 dash JX2 dash. This is the construction of tertiary winding, and here we have collect the secondary, and this is not connected actually. We will draw it in this way also. And this is the terminal of tertiary. Right. So this is the equivalent circuit. Now what we can write that it is between primary and secondary. Resistance R12, when you will conduct a test between primary and secondary, it is like R1 plus R2 dash. X1 is equal to X1 plus X2 dash. Now what about R23, that is R2 plus R3 dash, and X23 is equal to X2 plus X3 dash. So when you are conducting this kind of test, what you are doing, you are completely disregarding that primary part and you are treating secondary and tertiary. Between them you select either tertiary as your primary or the secondary as your primary, and the other one will be utilized as a secondary side, and you conduct the open circuit and short circuit test. Similarly, R31 is equal to R1 plus R3 dash. So Here, instead of writing all this equation, let me show you something interesting. Like in case of star without having neutral, it is difficult. Like if you have a star-star transformer. This star-star transformer now. This star-star transformer, yeah, this is primary, this is secondary. Now both the like no primary or secondary, both are not neutral wire is not available and neutral is not ground. Now if you connect a load here, what would happen? A current I1 will flow. Sorry, you can write it is secondary current, so I2 will flow. And correspondingly here what will happen? A current I1 will be drawn from the source, right? Now, okay, now let us consider that here the secondary side is grounded also. Let us consider that. Then what would happen? A current will flow. Now there will be a current. But after that, how this current will be divided among these two branches? Because here you can see that the current is flowing in this way, like it is finding a complete path. But here, when you are since their neutral was there, so current can flow find a complete path. But when you connect it, then what would happen? That there is no neutral, so when current will flow, that current will cause a flow of current through these two branches. However, there is no corresponding load present in the branch. So when this current will be flown through this branch, that will cause an imbalance in the voltage induced in these two branches, right? So that is a problematic issue. Just let me check. So what I was talking about, that this I1, due to ungrounded neutral or primary side, it will not find any path. So it will try to do what? It will try to find a path through these two winding. But for these two winding, those corresponding secondary is unloaded. It is like they will sense this current like magnetizing current, and that will cause a flow of rise of voltage across these two phases, and accordingly here this voltage will become will get a very poor voltage across this terminal. Why? Because here I2 is flowing, I2 is high, and the corresponding the adequate amount of magnetizing cannot be compensating element cannot be produced by the primary side, because primary side current is facing high impedance path. Due to this, it has to manage it path through this, but here it is getting an easy path. So you can understand that there will be a huge disturbance will take place, and this is not a hypothetical situation. In reality it can happen. Like instead of load, you can consider that you are having a primary, this is start transformer, and the secondary is grounded, and a fault take place across a what, like say this phase, a fault take place, and generally fault impedance is very low. they are having very small value of impedance, so they will offer a means very least amount of means opposition to that current I2. So I2 will be very high, and the demagnetizing EMF produced by I2, I1 will not be in means the magnitude of I1 will not be that high that can combat with the demagnetizing EMF produced by I2. However, the I1 again that will be in will means be these two paths, so that will cause another problem. Obviously, if you consider a grounded star, then there will be no such problem, absolutely no problem, because here also your current will find a path through this, and no need to means disturb these two remaining phase. Like if it is A, then current will, but if this neutral is not there, in that case current has no other choice than find its path through B and C. So that is issue here, and that is very disturbing. Now what we can do when we introduce stabilizing, so this is a case of unbalanced case. Now when we will do stabilizing winding, what will happen, like as a tertiary or stabilizing winding is present. Do remember that tertiary winding, they are always connected in delta, and their reactance value, we try to make sure that they are having a very small value of reactance, so that they can offer a high means admittance path to our third harmonic component. For sake of understanding, let us consider all these transformers are having 1:1 ratio. So if this current is I, then what would happen? Here, due to the presence of this stabilizing winding, it will carry I3 by current through its all phases, and therefore what we will have here, it is 2I3, this is I3, this is I3. However, you can see that now this I3, they are having corresponding term, so they are actually doing that kind of load balancing, and no such high voltage will appear across your means secondary terminal due to the presence of this tertiary. So let us solve a problem from our tertiary winding transformer, then that will help us to understand the concept clearly. So here is the problem. Three similar single phase transformers have their primary and secondary winding connected in star and the tertiary winding in delta. In each transformer, secondary and tertiary turns are equal. The ratio of primary and secondary turns is 2. The primary is fed at rated voltage by 3 watts. So 3 watt means it implies you are having ungrounded neutral, because whenever there is a neutral is present, you must have a 4-wire connection. With 3 watt means even if your primary is star, still it is not having a neutral available to you. So what is the situation? A single phase load taking 24 ampere and unity power factor is connected between one line and neutral. Calculate the current in each winding of the transformer In addition to the single phase load of part A, the secondary is now connected to a three-phase balance load requiring a line current. So we have to check. So how should we proceed? It's very simple. What we need to do is a simple thing, that is, you have to write the basic MMF equation I1 N1 plus I3 N3 is equal to I2 N2. So that will result as I1 plus I3 N3 N1 is equal to I2 N2 N1. So why a question may comes or should come in your mind, that why it is not I1 N1 is equal to I3 N3 plus I2 N2, rather I1 N1 plus I3 N3 is equal to I2 N2. That is an interesting question. I expect that question from you, and once you can convince me with your logic level, then only you can reach the answer. So what happened, that I1 is equal to I2 by 2 is how much? 12. So we got the scheme like here. It is our I1 plus I3 by 2 is equal to 12, right? Now let us draw the phasor, like not phasor, rather the schematic. Here is certain load that is consuming 24 ampere, right? So 24 ampere is circulating, so current in this path is how much? Uh, 24 ampere. Okay, fine. So these will lead to which situation, that if you think about MMF balance, what you will get, that either I1 plus I3 by 2 is equal to your, well, that we got. Now what more we can write, like if we consider the primary MMF, then the primary MMF due to, see here, primary MMF, that is, you can write how can we write this? Think about, see what we say, that your I3N3 and I2N2, they are having the same ratio, So from that we can write that I1 is equal to because N3 by N1 is equal to 1. So you will get I1 is equal to I3 is equal to 8 ampere and these two will carry 4 ampere. So that is quite a balanced distribution. The second part I wish that you will try by yourself and then one day we will discuss the solution of the second part, right?